It's my honor to invite Professor Subhas Mukhopadhyay. Mukhopadhyay, oh, that's good. Mukhopadhyay from Macquarie University. Professor Subhas is currently working as a professor of the mechanical and electronic engineering in Macquarie University, and is the discipline leader of the mechatronic engineering degree program. His field interest include smart sensors, sensing technology, instrumentation techniques, wireless sensors, and Internet of the Things, healthcare, mechatronics, robotics, environmental monitoring, and etc. Lots of things to talk about it. Hopefully, we got a chance to ask more questions with you. Thank you so much, please.
Thank you very much. So, good afternoon, everyone. And I actually like to start with thanking Manoj for organizing this fantastic conference. So last 2 years we were under pandemic, and this is a big step to make it happen. And today from the morning, we have such wonderful talks. And also last night dinner, it was really, really fantastic. So thank you, everything. So I have got like 20-25 minutes to talk about the research, what we do. And what I've seen, quite a few talks were really so much into the science. So I'll be looking a little bit on the engineering aspect. This conference effectively chemical and nanosensors. So I will not be talking most of the things on chemical sensors we do, but I will also give overview of the work what we do. So as you can see, the title is that effectively we develop sensors for better living. If we see the researcher as well as the applications, anyone without using sensors will not have a single day passed. Of course, researchers like us, we make sensors, but others use sensors. Without usage of sensors, we will not be able to appreciate our life. That's why Lord Kelvin told that if we want to improve something, we need to know what is the current value. That means we need to measure, and that measurement comes from sensor. So here you see many sensors we use in our day-to-day life. Some of them gives us values which can be measured, which can be stored, which can be transmitted. But many of them may not be giving you the value what actually you like to see. For example, if you see somebody likes to make cake, he has to use his vision sensor, eyes, so which will not give the electrical signals which we like to store or transmit. In my lab, we do two types of research. One type of research, we use the sensors which are available in the market. We connect them to electronic circuits, process the result, and put the data into the cloud. Other type of research, what we do is to make sensors. Of course, those who are doing research, they know that making sensor takes some time. So if somebody wants to do master's or undergraduate project, they go this category, PhD goes to this category. Our sensor we always call IoT-enabled sensors. That means whenever we do sensors, we do some measurement, we put the data in the cloud. And this is very, very useful for remote monitoring. We do not need to go to the sensing station where the sensor has been installed. This is the block diagram of the IoT-enabled sensors. We need the sensors. Sensor is the heart or the brain of any IoT systems. Without sensors, IoT does not exist. Many people, they actually analyze the data. They do not know where the data coming from. They also say that's IoT. That's actually not IoT. IoT means real-time measurement. So you need the sensors. But sensors data you need to process. So it comes with the embedded processor. Without embedded processor, we will be actually putting the data which may not be having some real value in our life. Next thing which is very important for IoT-enabled sensor is the internet connectivity. When we put the data in the cloud, without internet, it will not happen. As we are putting our data into the cloud, we are exposing it to everyone. We need to also think of the security. So sometimes when we actually do research in IoT-enabled sensors, inside the laboratory environment, everything looks very simple. But when we go outside, we actually can face a lot of issues. So we need to address that whether I have got the internet connectivity or not. If I don't have the internet connectivity, what actually wireless communication system I'll use? Can I go GSM? That is me running cost, all these things. And of course, the security. So for example, I will be talking the two projects which we have done recently. We use a network called the Things Network. That's actually a company in Sydney which called Mesh Network. That means we are using their service. And when we are using their service, we are putting the data, they own the data. Our data, we are generating the data, but they own the data. So interesting things. So those are the interesting things we will face. So I will tell a few minutes on our one project which we recently executed, Smart City project. Effectively, it's the pedestrian counting and ambient monitoring. Like Swinburne University, Macquarie also boasts having their own railway station. So a few years back, the train was extended and normal train was become a metro, and few stations between Epping and Chatswood, where the Macquarie University is one of the stations, the train was stopped for 8 or 9 months. We wanted to know how people behave during the disruption. So it's a disruption because Macquarie University having 40,000 students and 3,000 staff, so all total almost 50,000 people, maybe half of them coming by train. And if the train doesn't run, so it's a huge disruption. So you wanted to know how the people behave during this disruption. So what we did, we got a Commonwealth funded project. Project has a very big idea, but when we actually got the money, the idea changed, because if you think of that some company, for example, the telephone company, for example, the trains like Opal in Sydney called Opal, the New South Wales Transport, they promise they will give you the data. But once the project starts, you go and ask them, can you give your data? It's no personal data we cannot give you. So we had to change the project. So the project becomes how we can actually monitor or count people coming to the university from different convenience like bus, walking, and so on. So we developed the sensor node, which actually count the number of people. So in the beginning, we actually designed and fabricated using 3D printing. And one 3D printer, that casing took 26 hours. Engineering doesn't actually work very well there. So we had to change. So finally, we went to replace that casing with the normal box available in JK Electronics. So putting all the electronics, Arduino processor, wireless transceiver, LoRa gateway, battery, all these things in the box. And the counting was done using the PIR sensor. So that is the electric pole where our sensors located and the getting power from the solar panel. So we have 74 nodes installed around the Macquarie University area, counting the number of people as well as ambient parameters such as the direction of the people's movement, carbon monoxide, total volatile organic compound, as well as air quality data, temperature and humidity. And then we wanted to correlate whether that environmental data has anything to do with the number of people on the road. But then the pandemic started, so it is very difficult because you are under lockdown, you don't actually go, you don't have the freedom. But what we could see, one thing is that at the same place, the number of people on the road during lockdown and normal conditions is totally different, which is quite indications that things actually work. And another interesting observation, as you see, that during the lockdown, people's behavior is quite abnormal, not exactly abnormal, kind of irregular, that in the night time you can see people because they wanted to enjoy the freedom. I will talk another project which we are still executing, where is all water. It's a New South Wales government project. So this project is effectively what they want to see is that amount of water, the Sydney Water, who is the water supply company in New South Wales, they think that this much water we have and such water has used. So usually they have very good correlations. That's, I have got storage this much, I have got expenses this much, and I need to know that whether they are actually correct. But interestingly, they have found out that almost 25% water is missing. So the water is coming from rainfall, and also they have got their dam and other things. but then the water is used by the people, 25% of water is missing. So they want to know how this data 25% can be reduced by more accountability. So this project, five group of 4 universities, Australian National University, University of Sydney, University of New South Wales and Macquarie University, they are involved. Each one has got its own objective. For example, ANU, they have got satellite measurement as well as gravitometer, so gravitational sensing. UNSW, they have got the borehole types of sensors under certain places, and they want to know how the groundwater changes. And the Sydney University, they want to do the all modeling, how much water is coming, how much water is used. And then Macquarie University, we actually have the objective to develop low-cost sensor for real-time measurement with more spatial resolution. So we develop the sensor for temperature, soil moisture, soil temperature measurement, actual rainfall measurement, water flow, and all the data will actually go to the cloud for real-time measurement. And then we wanted to model called evapotranspirations. How much water is actually lost due to evaporations and how much water is actually absorbed by the soil due to transpiration. So that is our objective. So we develop sensors and we install the sensors. This is actually in the backyard, and then you install the sensor at a place called Narrabri, where Brady had been there for 3 days to install the sensors and putting the data in the cloud. And then, actually I forgot here to add some more. Then our objective is to make some more sensors where we will be installing them in a big area, and we want to measure and model how the water actually absorbed by the soil and the soil properties. So that type of things we are currently doing. So our sensor, what we develop, our big picture is to use them for human to make our lifestyle better, and what we call always the smart home, that whatever we develop, the sensor can be used by the persons and to make our environment better so that we can actually have much better life. And all these sensors are actually wireless sensors, so they measure the data and they transmit, and these days we can all call IoT-enabled sensor. So sensor what we fabricate, so the last 2 projects, basically we use the sensor which is available in the market, we make them as a system, but sensor what we fabricate is interdigital sensors. So I'm working in this area almost last 15 years, and this interdigital sensor I have seen today, whole day, many talks, they were actually also interdigital sensors. This interdigital sensor is very, very useful for measurement of any kind of dielectric material. So dielectric characterization. So whether you measure any kind of food related particles, water related, meat, anything. And they work on the based on electric field. So electric field pass through the material and test, and the impedance is measured. This impedance actually tells you about the properties of the material you want to measure. And what we do, we actually take both the capacitive part as well as the resistive part. So I was actually talking to the poster, they only take the resistive part. I think they are missing one parameters, because the capacitive part is also very, very important, and that's the most important thing, not the resistive one. So we, as you have seen this project, this is the 4-inch wafer. Interestingly, very fast sensor when we fabricated. My student, he took only the middle. Only 4 sensors we used, 2005 or 2006. I still remember all the things that no, they are not good because the middle part. But then when we used the laser ablations and we got 35 sensors, only the edges were actually not correct. So of course, this is the process who are involved in fabrication step, they know. So that's the process we have to do. And when we get one sensors, we can actually use them. So the sensor size is around 2.5 millimeter by 2.5 millimeter. The spatial resolution is 25 micrometer, and the total is 10 millimeter by 10 millimeter. Before we make the embedded processor-based system, we actually characterize the sensors. For characterization, we use the LCR meter, which is very common for our applications. And then, of course, we go for embedded processor-based sensing system. And we can go to complex equivalent circuit, but the most simple equivalent circuit for integrated sensor is the measurement of impedance. We have only one series resistance, apply some alternating signal of desired frequency, and then you measure the current, and then measure the impedance, and measure the phase angle. You get the capacitive part and the resistive part, and then you measure your properties. So the very first project, based I think almost 2009-10 times, we actually developed E. coli detections using these sensors, and then of course these sensors is very, very sensitive. And the sensitivity part we can improve by the dimensional changes. So the size, length, and the spatial resolutions. But of course, as we know, all the sensors, they have to have the property called selectivity. Without selectivity, the sensors are useless. And that's what today's talk, there are many talks where talking about the selectivity measurement. So for the selectivity of E. coli bacteria, we use antigen antibody method. That comes as a functionalized material, as a coating surface on the top of the sensing material. Now this coating, you can do different coating methods, either deep coating or spin coating or electrospinning. So we have tried all the methods. So here I'm just showing the picture of the deep coating method. And the deep coating method, of course, we follow certain steps. We have to dip the sensors into the coating material. And of course, we follow some speed and so on and so on. And then after dipping, we rotate it. And then we actually can tell how much is the thickness of the coating. And that we use atomic force microscopy to measure how much is the thickness. And that thickness plays important role. How many times you can actually use your sensor to measure the contaminant. Later on, we moved to develop another type of coating material based on molecular imprinted polymer. So this molecular imprinted polymer is having some advantages that you can actually prepare it and then use it for a long time. So as I noted down here that they are having quite a few advantages, and it's like that when you play musical chairs, one chair is empty, people running and then want to sit down on the chair when the music stops, exactly similar. So we make this molecular imprinted polymer, then we actually extract the target molecule. And once we extract the target molecule, then we functionalize it on top of the sensors. And then we pipette the actual sample, then that molecule empty space is covered by the molecule in the sample. And then it reflects in the change of impedance. So in the last few years, we have done different projects. This project was for the brain tumor. So when somebody has the brain tumor, doctor operates. After that brain tumor reoccur. So that time when the person goes through the chemotherapy, we have seen doctors told that there is a change of creatinine level. So you can measure the change of creatinine level using the sensors from the blood sample. So this is one project. Another project is that leaching of plastics called phthalate from plastic bottle. Interestingly, as we know that water is very important, but water doesn't have any expiry date. But when water is stored in the plastic bottle, we actually have seen that there is a date of expiry because this plastic leached from the bottle to the water, and that can have a health effect. So that's what we did this project, and actually we could measure up to 2 parts per billion. Another project was detection of the early detection of the osteoporosis. So osteoporosis is the basically bone loss, and in Australia, 1 in 3 women and 1 in 4 men after 50 is having this issue. And osteoporosis is a huge expenses for Australia. Almost $33 billion they spend over 10 years time on the treatment. But if we could detect at early stage, then it can help a lot. So this one, again, this project, what we have done is using this molecular imprinted polymer technique, and we detect the type 1 collagen called C-terminal telopeptide. That's the biomarker we use here. And again, this is a IoT-enabled system putting the data. And at that time, 2019, when my student finished, we thought that we could make it as a sensor array, detecting the C-terminal telopeptide, calcium, and also creatinine to tell, and you do not need to collect sample. You can put the sensors on the toilet and it will be automatically done. And that time when I have one paper, I thought this is a dream. But interestingly, we could not work on that, but I can see some paper. Last month, when I'm the topical editor of IEEE Sensor Journal, I saw one paper submitted. So I was feeling very happy, at the same time sad, because I could not do, but somebody has got the idea and doing that. So that's the situation now. So here, like Brady is there, so he has done this one called sensor for aqueous sulfur. This is important from the point of view of the wastewater pipes. So in Sydney Water in New South Wales, they want to know before the pipe cracks. And they have identified that if we could detect the H2S gas, then that will be very, very helpful. The early detection of H2S gas. So this one is the aqueous solutions of this sulfur gas, and we think that it can lead to detection of the H2S gas. And the sensor, we have the same interdigital sensors, but we have got here, as we can see, is reduced graphene oxide with silver nanoparticle as the coating layer. And the selectivity part, of course, we can say is not ideal, but it is more responsive to sulfur compared to other calcium, magnesium, and phosphate. The another one is the detection of the ethylene at ambient temperature. Again, here also we use interdigital sensors and as a reduced graphene oxide with the as a coating layer. But again, as you can see here, that we have selectivity at ethylene, but also other gas also getting detected to certain extent. Last 3-4 years, we are working on the flexible material. So we develop the sensors, again, interdigital sensor using flexible material, PDMS, polyimide fill, PET as base, and then of course, graphite, carbon nanotube are there as the electrode material. And we have fabricated many sensors for different applications. It can come as a part of the clothes for the body movement and other types of applications. Also, it can be used as a robotic applications to know the position of the robot, movement of the robot, environmental applications, and so on. And this one, the iron nitrate sensors, I'm working on this for quite some time. So here, what we do again, the sensor is iron sensors, and the sensor can detect nitrate. And again, we develop the coating material. But all these things are very good in the laboratory environment. So when it goes to the field, then the problem what we face is that because you are dipping the sensor in water, after few usage, this coating material goes away. This is the biggest challenge we face. So things are very good. If you think of that sensor is one-time use, you fabricate the sensor, you use one time and throw, or in the laboratory environment where you have the opportunity to coat it again and again, they are all very good. But when you go to the field where you want the sensor to last not few days or few hours, it actually need to last few months, then is the biggest challenge. So this one like worked very well. We have tested, and we recently now started that can we use machine learning without having the coating, just the interdigital sensors to tell us about the measure value. So of course the machine learning, we have to train the systems, but if we could train properly, then we can see that we could actually do, and that's what we have done. And to extend the lifetime of the sensor, what we have done, instead of dipping it in water continuously, we actually dip it only when we measure. So we pump in water, measure it for a few seconds, and pump out the water. And that helps us to extend the lifetime of the sensor. This is another project which we are currently doing with the University of New South Wales, is for monitoring the lower back pain of lumbar interbody fusion. So that's coming in the spine. Of course, it will be not used at this stage because we have to go through a lot of ethical approval. So the sensor will come here, how the interbody cage is actually aligning with the bone and the muscle. So that's the sensor we have fabricated. And we have done a lot of tests in the offline with the simulated environment. And we got very good result. But now at this stage, we actually filed a patent last year in Australia. We are now waiting for some more testing. And another work which we are currently doing is the large skin, which will be simulating the human skin for good resolution and sensitivity. So anyway, I will freeze here because of the time. So effectively in my lab, what we try to do, we try to develop sensors for different applications. Most of the sensors is actually some kind of coating. It can be defined as chemical sensor or biosensors. In real life applications, they really work well inside the laboratory environment and to a certain extent in the field. But in the field, there are lots of challenges we face. And in order to make them happen to real practical field applications, we need a lot of testings and making the sensor robust and rugged. So thank you very much and happy to take any questions or comments.
Thank you so much for this great presentation about the actual real-world application of the sensor. So we are happy to take a couple of questions. All good. I will go first.
Yes.
About when you are making these sensors, these are just a normal nano arrays of the with micron size.
Interdigital.
Yeah, like a comb array beside of each other. How do you functionalize the special molecules on the top? So when you want to make it selective, for instance, when you are talking about a disease in the blood, you need to filter the blood, you need to get the plasma out, or is it the direct droplet?
Yeah, actually,
how do you make the...
No, we don't need to do anything. We just put the direct drop of blood.
So you are not separating anything
No.
from it? Oh, okay. So
but that's what you have to functionalize. So polymer which you develop, that will be selective to particular. So whether it's a protein, whether it's other molecule. So you develop this polymer and then you functionalize. So for functionalization, you have to use some kind of chemicals which will stick together. And then you put the drop of blood or whatever you have.
So the polymer that you're using, it is a conductive polymer, right? Or a semiconductor polymer that you're putting inside?
So that comes as a mixture of different things.
Different things, okay.
So that may be to a certain extent conductive, maybe not. So depends on, so when you actually develop the polymer, you need to know which is your target molecule.
Yeah.
And that target molecule you have to have as the
imprinted
preparation
in the...
imprinted.
Wonderful, wonderful.
So we have checked. We have developed the polymer without printed molecules and with printed molecules. But interestingly, non-molecular also give you response, but the response will be low. So it's not very highly selective. But
it is depends on all the stretches as well as the temperature of the process, right? Because
temperature, this sensor, intelligent sensor anyway, temperature is highly dictating your response.
Of course.
So you have to develop some temperature compensating circuit.
You're imprinting the molecule, so the dimension of that imprint can be changed based on the...
Dimension of the imprinted molecule will be totally dependent on the molecule you want to detect.
Okay, wonderful. Thank you. This.
It was intriguing by saying that we are losing some information if we are not measuring capacitance. Right? So can you a little bit more elaborate? So what is information which is important for sensing application if only resistivity?
So basically, if you see this interdigital sensor is the electric field sensor. So electric field passes through the material under test and impedance changes. So that impedance, because it's the electric field, is basically the capacitance. Capacitance is related to electric field. So many people, they actually take the resistive part. So resistive part will be whenever there is a change of ionic things. But it might happen that it's not ionic. It's a dielectric permittivity. So that means you are changing the capacitance, but you are not able to get the resistance because it's not ionic change. So only when there is ionic change, that will be reflected in the change of resistance. So we do not actually bother about the resistance. What we bother is the capacitance. But what we have seen, the resistance also changes when it becomes little bit ionic. So the resistance change may be very little, but capacitance change will be very significant. So if people do interdigital sensor and they only go for the resistive change, that means they are missing huge amount. And also another important thing, if you get one measurement, you get two parameters. So that's also another important thing.
Thank you so much. Let's thank again Professor Subhas for the great presentation. We enjoyed a lot.
Thank you.